All right, if y'all are done over there, just leave things where they are and I'll clean them up later so we can get to our lesson, okay? All right, y'all done? Yeah, it's people that are this way don't even realize there's somebody here, so you kind of have to be like, hey, it's him here, sorry. Just stick it anywhere in there that there's room for now, or leave it in your bin if there's no room. All right, guys, let's get our lesson going. So if you're still working over there, just set it aside. We have all the data now, so we got what we need. Is that door shut? Or did you leave it open? Did you tend to leave it open? It's fine. Straight cheese is crazy. Dude, I love straight cheese. I'll eat it. All right.
I do that all the time. I eat cheese.
Oh, God.
It's pathetic.
It's behind you. Oh.
Yeah.
I think it's shadow.
Your trust in my upholstery's cleanliness is admirable. So shall we commence? All right, so order and spontaneity is today's lesson. So let's talk about enthalpy in reactions, which is what you just measured. Close that. What you just measured in lab today. So if you remember, there's a lot of architectural images in these slides because, I don't know, something about the whole idea of order and organization made me think about cool black and white architectural images. So anyway, that's what we got going today. So enthalpy, changes in enthalpy accompany reactions. So remember that changes in enthalpy can be one of two things. What can they be? The change is either what or what? It's the heat that we measure, but it's what? It's thermal energy, but what do you get for that, Colin? Positive or negative. So positive, you would expect something to release some heat, and negative, right? Obviously. So temperature impacts enthalpy change. So often reactants and products are presented in equations at standard what? Well, how do we measure this? What kind of temperature do we use, Caitlin? We do use, yeah, we use Celsius in lab, but we're looking at room temperature. We're looking for standard thermodynamic temperature. Okay, and we do have a certain standard for that, which we'll talk about here. So standard thermodynamic temperature is the absolute measure of what in an object? What is it measuring? When you measure temperature, temperature is the measure of an object's. There you go. Very good. So your average kinetic energy. So our standard thermodynamic temperature is the average of the total energy in an object or objects. So now we're talking about like a system, namely its kinetic energy, which is energy of motion, like Caitlin just said, kinetic energy, plus contributions from other factors. There's sometimes some other things involved. So today, if you took good measurements, you probably would have found that all of your liquids would have been close to the same temperature. At least on your thermometer, it would have been close to the same temperature, which means that a change in temperature, like if your thermometer is different by, because, we talk about precision for tools, right? Not everybody's tool is going to be the same. Like I know if I go to my doctor, their scale's off by 3 pounds and they just add or subtract that from your measurement, whatever it is, because they know that that's the case. It doesn't change. The delta is going to be the same no matter what, because we talked about in Hess's law, right? The coefficient thing, the whole issue of it's an algebraic problem, right? If you're multiplying everything by 3 on one side, then you have to multiply everything by 3 on the other side. So your change is not, your delta isn't going to be different. So everybody's delta despite what your degrees Celsius, your measurements should have been, everybody's deltas should have been close to the same if their reactions all worked accordingly. So we express this in when we're talking thermodynamics, what scale are we using? Number of what above zero? What scale are we using? Do we know? 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 Caitlin, you want to hazard a guess?
Yeah. Absolute zero.
Yes, so there's your hint. Yes, so it's expressed in your number of kelvins above absolute zero. When we do when people that work in thermodynamics, they love Kelvin. They hang out in Kelvin all day long. It means so little to me because it's not something that we use in our day-to-day life, right? We don't use Kelvin. If somebody told you it was, 20 degrees Kelvin, you would have no idea what that means for you, like in your day-to-day life. Like it'd be real cold, yeah. So a typical thermodynamic standard state in normal laboratory is normal laboratory conditions. So about 25 degrees Celsius, which is about 70-ish Fahrenheit, or 298.15 Kelvin. Okay, so there's a clue. 200, so almost 300 Kelvin is your room temperature. So it's like close to 300 Kelvin in here. But that doesn't mean much to you, like, because you don't use it, right? Unless you work in thermodynamics, then you use it every day. So at 1 atmosphere. So this temperature and pressure at the same, we have to measure at 1 atmosphere. That's what we assume, okay? And what do we call it? There's an abbreviation for it. It's standard temperature and pressure. So we call that STP. But it's not this STP. You seen this one before? This is for racing. This STP. If you watch NASCAR or any kind of racing, you may have seen this before. And then it's not this STP either. Do y'all know the Stone Temple Pilots? People often call them STP too. So standard temperature and pressure.
I've never heard them.
No? Oh my gosh. Everybody I grew up with called them
I've
STP.
only heard them ever called by the name.
The Stone Temple Pilots. That's a big name.
Or like just
Big.
pilot.
Oh, well then there's 21 pilots. How do you know which group you're talking about? You talking about, yeah, which one are we talking about? I don't know. That's cool though. All right, so this is a strange image. Welcome to the weirdness of historical science again. We'll get to it. It is a dog. We'll get to it in a minute. Promise we'll get to it. So what's the experimental measure of enthalpy? So this is calorimetry. This is what you did today. You did an experimental measurement of enthalpy. And remember that enthalpy is the energy within a system, but you can't measure the energy within a system. You can only measure what? The change in energy in a system. And that's your change in enthalpy is really what you're paying attention to, right? Because that is measurable. Whereas just measuring the energy, you really can't. You can measure the change. So we call that calorimetry, and it's an experimental measurement of enthalpy. What did you call that thing that you used today, PJ?
CBD.
No, not the CBL. We didn't use it. Although, okay, yeah, we know where your mind went today. It's all good. So, you were thinking the CBL. That was the thing we didn't use. But what was the little apparatus that we use? Calorimeter, right, James? Calorimeter. So I know there's a little spider floating around in here. Let me see if I can let her out real quick because she just wants to.
That's so cool.
I'm also in that room.
I was trying to find the little living things out of there.
Because I told the spider.
She's gonna slow down real fast out there. In here, she's like, wait, fun. She gets out there, she's gonna be real cool. Okay, calorimeter. So again, we have calorie, which is heat, basically a measurement of heat. Meter, calorie is a measurement of heat. So when you think, okay, you just ate something. So when you look at how many calories are in that package, Ridley? 160. Okay, now here's the thing. Those aren't actually calories. Do you see how it has a capital C? Yeah. Okay, capital C calorie is 1,000 calories. So how many calories, lowercase c, are in there? Yeah, fun, right? There you go. So when you see calories on food, it's capital C, and that means 1,000. calories. All right, so types of calorimeters. We have, do you know what it's called? The type of calorimeter that's used to measure a runaway reaction. Any heat generated by the sample under test causes the sample to increase in temperature, which fuels the reaction. This one is an adiabatic. I always have trouble with this one. Adiabatic calorimeter. And then we also have the kind that are used to measure combustion reactions, and those are oxygen bombs. So which kind did you use today? Did you have a combustion reaction? Yeah, so we had adiabatic. That's what we use today. All right, so you're wondering what is going on here. So calorimeter studies of Regnault, 1810 to 1878, combine the measurements of heat production and gas exchange by small animals in everted bell jars of the Hales gun barrel design. That's what this is, this everted bell jar of the Hales gun barrel design. And a eudiometer was used for gas analysis. Heat production was determined by immersing the bell jar in a constant temperature bath. And this was the first experiment to directly equate carbon oxidation and heat production in the same animal. You produce carbon dioxide when you exhale. You also are producing heat. That is coming from the same chemical reaction, which is what reaction? Cellular respiration, yes, or aerobic respiration. And we had not, up until this point, been able to equate the heat production with the carbon dioxide production. But this dude stuffed little puppies and critters in bell jars and let them breathe and measured their temperature and their gas exchange and was like, oh, look, I can make a correlation. So I'm pretty sure that little scruffy thing came out of there okay, but he spent some time in there for a little while breathing and whatever. Yes?
Did you get things off?
You know, I doubt they got days off. I don't think there were small animal unions then to, you know, work for that for them. So they probably did not take days off. And they were probably captured off the street or whatever else, because that's so ethical. Okay. So here's our man. Here's our man Hess. So this is the guy responsible for the equation you're going to be doing to complete your lab. So the change of enthalpy in a chemical reaction, which is the heat of the reaction, okay, at constant pressure is independent of the pathway between the initial and final states. Do you remember the car, the Ghostbusters car from the video last week? It went down the hill. The pathway was down the hill, and like, depending upon the speed he went down the hill, he smacked into the lemonade stand or whatever it was with more or less force. Banana stand, something like that. Yes, right. Okay. That was talking about the pathway. So this is independent of the pathway between initial and final states. So your heat is going to be produced no matter how you get there, basically. All right. And your overall enthalpy of a reaction is equal to the sum of what? This is what you did. This is what you're going to be doing, Jordan.
Some of all the changes in them.
Yes, all the steps, right. It's the sum of your individual steps in your process. So what you did today was you took, are you all right? You took your process and you broke it down into smaller steps and you measured the change in heat at each step. And if you add that up together, it should be equal to your change of your entire, or it should be close, change of your change of heat for your entire reaction. Are y'all all right? My goodness. So this is what that looks like if you do it symbolically. So you've got a delta in heat, right? This RXN would be reaction, right? And then, yeah, there's your sigma again. You gotta love it when the sigma shows up. But if you go into a career in thermodynamics, you'll get real familiar with this type of work. We don't need it for our purposes, but know that it's a thing. And it's how we get some of the numbers that we get these days. So basically, if you have, basically the point is that it's also reversible, right? We saw that today, or we would see that if we did. Well, we saw that earlier because it talked about it in the lab. All right, so Hess's law is your heat of summation. Like I told you, my brain is like, yep, can't even talk today. All right, so let's watch this one. Are y'all getting out of control? Man,
There's probably several different ways that you could take to get from your house to school. But if we were just to take a straight line from your house to the school, your overall displacement, regardless of which pathway you took, is going to be the same. Now, chemical reactions can work much the same way. That is, if our reactants serve as the start for our pathway and our products serve as our end result for our pathway, there are possibly multiple ways to get from our reactants to our products. And if our goal is ultimately to figure out what the overall enthalpy change is for a particular reaction, and we can figure out what the enthalpy changes are, or if they're already established for those pathways, then we can use the knowledge of the enthalpy changes for those pathways to figure out the overall enthalpy change for our target pathway. And this is what's known as Hess's law. And Hess's law basically states that the overall enthalpy change for any given chemical reaction is independent of the pathway that it takes to get there. Now, why this is important is because for some reactions, it's not very easy to collect empirical data, meaning it cannot be easily done in a coffee cup calorimeter. Imagine those scenarios where the reaction doesn't take place in an aqueous solution, or it's too energetic or too slow to perform effectively in a high school laboratory, or perhaps there are additional reactions that go along with it, and there are byproducts or additional products that are going to be produced. If we're trying to analyze the overall enthalpy change for a target equation, it is possible, if given information about already established reactions that lead us to our products, that we can use those already established reactions and Hess's law to establish the overall enthalpy change for a target equation. Now, if you've studied combustion reactions at all, you will know, especially with carbon-based fuels, that one of the products that we're going to get is often carbon dioxide. But you may also know that one of the other products that we can possibly get is carbon monoxide. But it's difficult, especially in combustion reactions, to isolate just the production of carbon monoxide and therefore the overall enthalpy change that we're going to have, because most of the time there's going to be byproducts of, say, carbon dioxide form. So it then becomes very challenging for us to establish the overall enthalpy change for this particular equation. But we can use Hess's law to figure out what the overall enthalpy change for the combustion of carbon producing carbon monoxide is going to be if we know some alternate pathways. So let's take a look at an example that involves just this mechanism. So what we are going to see here is that we have an equation that involves 2 moles of carbon combusting in the presence of oxygen to produce 2 moles of carbon monoxide. Typically, with Hess's law, we are provided with a couple of known equations that already have known enthalpy changes. So for example, we have an equation 1 in which we have the combustion of carbon to produce carbon dioxide. In equation 2, we have the combustion of carbon monoxide in the presence of oxygen to produce carbon dioxide. Now notice that we don't need the carbon dioxide here, but that's going to come into play later on. Our first step is to rearrange these equations in such a way that the reactants are on the reactant side and the products are on the product side. So if we take a look at equation 1, we can see that carbon and oxygen are both on the reactant side, just as we need for the target equation. And if we take a look at equation 2, we can see that carbon monoxide is on the reactant side, which is actually opposite of what we need for the target equation. So what we're going to do is we are going to effectively reverse equation 2. That is, the reactants become products and the products become reactants. Now notice if we do this, what we have to do is also change the sign. So remember, any manipulation you make using Hess's law to the equation, you also have to make to the overall enthalpy change. That is, if we reverse it, we also have to reverse the sign. So something that is exothermic in one direction becomes endothermic in the other. Now in reversing this sign, what we can see is we now have carbon monoxide on the product side. So we have our carbon and oxygen on the reactant side, and we have our carbon monoxide on the product side. Now, it looks like we have oxygen both on the reactant and product side, but that's actually going to play into our favor a little later on. So now that we have the appropriate substances on the reactant and product side, what we have to do is take a look at the coefficients. That is, we have to make sure that the overall equation is balanced. So notice that in equation 1, we only have 1 mole of carbon, whereas our target equation requires 2. So what we are going to do is we are going to double our equation number 1. Now what that's going to do is provide us with 2 moles of carbon, 2 moles of oxygen, and 2 moles of carbon dioxide. And just as we had to reverse the sign for the manipulation we made to equation 2, since we're doubling the amount of carbon and the amount of oxygen and the amount of carbon dioxide produced, we also have to double the overall enthalpy change for this equation. Now, if we take a look at equation 2, you may also see that we're going to have to double it as well. Our target equation requires 2 moles of carbon monoxide, and yet we only have 1 mole of carbon monoxide being produced in equation 2. So by doubling it, we now have to double not only the carbon monoxide, but also the oxygen and the carbon dioxide, as well as our overall enthalpy change. So not only has the enthalpy change for equation 2 changed its sign, but we've also had to double it. So the full name for Hess's law is Hess's law of heat summation. So what that allows us to do is add up everything that we see here to analyze what's on the reactant side and what's on the product side, as well as the overall enthalpy change for the target equation. But we can make things a little bit easier on ourselves before we even do that. Notice that we have 2 moles of carbon dioxide on the reactant side from equation 2, and we have 2 moles of carbon dioxide on the product side from equation 1. So effectively, if we were adding these 2 equations up, these 2 moles of carbon dioxide are going to cancel each other out. Similarly, what we can see here is equation 2 has 1 mole of oxygen on the product side, and equation 1 has 2 moles of oxygen on the reactant side. Effectively, that means that 1 mole of oxygen didn't really do anything or didn't participate in the reaction, so we can cancel that out as well. And notice that if we cancel out the carbon dioxide and the oxygen, then what we're left with is if we add up the remaining species on both sides of the arrow, we're left with the target equation. Now, the last thing that we have to do is take the enthalpy changes of equation 1 and equation 2, add them up, and that's going to give us the overall enthalpy change for our target equation. So hopefully, if you were paying attention to that example, it helps a little bit in how we practically go through manipulating established thermochemical equations and manipulating their enthalpy values in order to find the overall enthalpy change for a target equation. Now, I should note that there is another way that we can utilize Hess's law using something called heats of formation, but we'll save that for another video. Thanks for watching.
So your lab
Let
is,
someone-
a much more simplified version of that, where you're doing step and step. And if you watch I get people that are like, I'm stuck, I don't know what to do. I'm like, did you watch video? Like the video will step by step by step take you through. Who's watched the videos so far? If there's a lab video and you need to turn in a lab, have you guys taken advantage of watching the video if it's available? If it's available, watch it. I mean, usually the calculations are on the screen, so you can check and make sure you're doing the right thing. Obviously, your data is different, so you're using different numbers when you're calculating, but the process doesn't change, right? And that's why they're there, is there to help you out. So if you're like, okay, I don't know what my next step is, it should help you with it. All right. So you have an idea what Hess's law is? It's if you take the reaction and you break it down into smaller steps, you should be able to add those steps up and it will give you your total change in enthalpy. So that's kind of as far as we go with enthalpy. We don't do much more than that with enthalpy at this level of chemistry. But now we're talking about order and spontaneity. So different topic, similar word. Are y'all too? Am I going to have to move? Or are you going to be able to focus? Okay. All right. Now we're talking about entropy. So like I said, similar word. So it's the measure of your disorder in a system, entropy. Now, last year in physical science, we touched on thermodynamics. We're going to go back and touch on that exact same lesson towards the end of this lesson, because it should remind, if you were here before, it'll remind you. And if you're not here, you'll be like, oh, that's new. But it'll remind you of the laws of thermodynamics, why they function the way they function, and how that's involved with order as well as spontaneity. So it's a measure of the disorder in a system. So what do we call, what kind of property is it? Do you know, Jordan? So you may not, it's a thermodynamic property, which is what we're getting at. Okay. So it's measured in joules per watt. How do we measure entropy, PJ? No? Colin? Joules Kelvin. Very good. There's our Kelvin again. So these guys that do thermodynamics, entropy, enthalpy, they love Kelvin, remember? All right. It's also represented as S. Now you'll see on your in your weekly email, there will be a little note about how you can prepare a 3x5 note card for your midterm. And one of the things in there is you can put in variables and the values that they represent, or not the value, but what the variable represents. So you can put like S equals entropy. That's an okay thing to add. It's a very specific list of what you can and can't put on your note card, but this is an example of something you could. Like Q equals heat, S equals entropy. You could put that down. And what does S with a 0 superscript mean? So that's your standard entropy, okay? And that would be what delta S would be. Jordan, change in entropy. Yeah, there you go. So if your entropy is positive, so if positive, what happens in entropy and is more likely to occur as it allows for increased organization? Do we know what we want here? So it's an increase. All right, so this should help you with the next one. If your change in entropy is positive, it means there's been an increase in your entropy and it's much more likely to occur because it allows for increased organization. If it's negative, then what do you think has happened to your entropy? It's decreased. Okay, good. Context clues. So your reaction is your entropy of the products minus the entropy of the reaction, of the reactants, gives you your entropy of your reaction in general. Okay. So this is a great explanation of what entropy is, what it means by order and disorder. Oh, look, we're going to get a Google shopping game commercial. I don't know what that's about. Woo! At least we're done with political ads. Now they're just Christmas shopping.
I love having the
Hi.
vegetables with my mini net 780.
That was fun.
I've always watched my sugar levels really carefully, but with the meal detection technology,
What is
delivering
happening?
automatic correction boluses every 5 minutes.
When you
I
talk
can-
about this is.
Oh.
Now we're looking at restaurant.
Hold on, that is really freaky. Hold on.
I'm living more freely and spontaneously with my mini net.
Yeah, I know. You're somebody with diabetes. Clearly. Where did you come from? Who are you? Where did you come from?
I got hat.
Good job, Jeffrey.
That is so weird. Okay, I don't know where that came from. That was very weird. All right.
There's a concept that's crucial to chemistry and physics. It helps explain why physical processes go one way and not the other. Why ice melts, why cream spreads in coffee, why air leaks out of a punctured tire. It's entropy, and it's notoriously difficult to wrap our heads around. Entropy is often described as a measurement of disorder. That's a convenient image, but it's unfortunately misleading. For example, which is more disordered, a cup of crushed ice or a glass of room temperature water? Most people would say the ice, but that actually has lower entropy. So here's another way of thinking about it, through probability. This may be trickier to understand, but take the time to internalize it, and you'll have a much better understanding of entropy. Consider two small solids, which are comprised of 6 atomic bonds each. In this model, the energy in each solid is stored in the bonds. Those can be thought of as simple containers, which can hold indivisible units of energy, known as quanta. The more energy a solid has, the hotter it is. It turns out that there are numerous ways that the energy can be distributed in the two solids and still have the same total energy in each. Each of these options is called a microstate. For 6 quanta of energy in solid A and 2 in solid B, there are 9,702 microstates. Of course, there are other ways our 8 quanta of energy can be arranged. For example, all of the energy could be in solid A and none in B, or half in A and half in B. If we assume that each microstate is equally likely, we can see that some of the energy configurations have a higher probability of occurring than others. That's due to their greater number of microstates. Entropy is a direct measure of each energy configuration's probability. What we see is that the energy configuration in which the energy is most spread out between the solids has the highest entropy. So, in a general sense, entropy can be thought of as a measurement of this energy spread. Low entropy means the energy is concentrated. High entropy means it's spread out. To see why entropy is useful for explaining spontaneous processes like hot objects cooling down, we need to look at a dynamic system where the energy moves. In reality, energy doesn't stay put. It continuously moves between neighboring bonds. As the energy moves, the energy configuration can change. Because of the distribution of microstates, there's a 21% chance that the system will later be in the configuration in which the energy is maximally spread out. There's a 13% chance that it'll return to its starting point, and an 8% chance that A will actually gain energy. Again, we see that because there are more ways to have dispersed energy and high entropy than concentrated energy, the energy tends to spread out. That's why if you put a hot object next to a cold one, the cold one will warm up and the hot one will cool down. But even in that example, there is an 8% chance that the hot object would get hotter. Why doesn't this ever happen in real life? It's all about the size of the system. Our hypothetical solids only had 6 bonds each. Let's scale the solids up to 6,000 bonds and 8,000 units of energy. And again, start the system with 3/4 of the energy in A and 1/4 in B. Now we find that the chance of A spontaneously acquiring more energy is this tiny number. Familiar everyday objects have many, many times more particles than this. The chance of a hot object in the real world getting hotter is so absurdly small, it just never happens. Ice melts, cream mixes in, and tires deflate because these states have more dispersed energy than the originals. There's no mysterious force nudging the system towards higher entropy. It's just that higher entropy is always statistically more likely. That's why entropy has been called time's arrow. If energy has the opportunity to spread out, it will.
So systems have a tendency to become more organized or disorganized. More disorganized. Why? What was the last thing he did? If energy has a chance to spread out, it will.
He exploded.
Right? Yeah. So things have a tendency towards disorder. So think about your ice cube versus your water versus your water vapor. Okay. There is more order in the ice cube because all of the particles are kind of locked into place. They're vibrating, but they're in place, correct? Think about it. All your little particles, they're all a little tight inside of their solid state. You add energy to the system, they do what? They spread out, right? They're becoming more disordered. And then again, gas is even more disordered, right? Those particles, I told the juniors this morning to think about the particle situation in solid, liquid, and gas as like a dinner party where everybody's sitting in their one place. That's your solid, right? Not everybody's very orderly. And then your liquid would be like a party where you're mingling. You're walking about and saying hey to friends. It's you're mingling, you're flowing. And then your gas would be like a rave, like they're bouncing off the walls. A lot of disorder there. That's a ton of disorder. Like if you went into like a nightclub and saw everybody on a dance floor, you would not go, oh, this is so orderly. Like that would not be your thought, right? There's higher energy, there's higher disorder. And people tend towards disorder too, if we're being honest, right? And I bet your bedroom does. If you don't keep your bedroom in check, what happens to your stuff?
It died.
You tend to disorder. Everything tends to disorder. Systems will tend to disorder. So now we have this guy Gibbs. Okay, and Gibbs talks to us about Gibbs free energy. I want you to know and understand what this is. We're not going to apply it a whole lot in this level of chemistry, but it's important to understand. So it's that the energy associated with the chemical reaction, and it's what's used, excuse me, to do the work. So it's the free energy in a system, which is the sum of the enthalpy, which remember We can't really measure enthalpy. We can measure changes in enthalpy, plus the product of the temperature in Kelvin and the entropy of the system. So they call it a free energy of reaction. So what does it predict, do you suppose? Yeah, spontaneity. So similarly, yes, spontaneity. And if the Gibbs free energy is what? The reaction is going to be spontaneous. Do we think positive or negative? If it predicts spontaneity, if Gibbs free energy is positive or negative, what do you think? Think if it's negative? Anybody else think it's positive? What do we think? Jordan? He thinks positive. What do you think? Positive. So if it's negative, the reaction was spontaneous. So that's how these work. That's how his come out. And when you do the mathy math, you're looking for negative to produce spontaneity. So a spontaneous reaction is a reaction that favors the formation of products at the conditions under this. It looks like that. Okay, again, more mathy math stuff. So there is a way to make some predictions, and this is the guy who helped us figure that out. No, that's a thing. So entropy and enthalpy determine Gibbs energy. So here is your enthalpy. Here is your entropy, and it gives you your Gibbs free energy. So you have a change in free energy, and it is the change in enthalpy minus the temperature and the change in entropy. That's how you get your Gibbs free energy. So what does that mean? All right, we're gonna let our friend explain it. Our good friend, huh? Gibbs free energy. So he does a great little explanation here. Ooh, it's time to shop for Christmas. Yeah.
Professor Dave here. Let's learn the laws of thermodynamics.
Woo!
The laws of thermodynamics help us understand why energy flows in certain directions and in certain ways. A lot of the concepts described by thermodynamics seem like common sense, but there is a layer of math beneath the intuitive level that makes them very powerful at describing systems and making predictions. We won't get into the math, but we should be able to describe these laws conceptually. The first law, described in the most basic way, highlights conservation of energy. Energy is not created or destroyed, it only changes forms, from potential energy to kinetic energy to heat energy, etc. While we have found this to be untrue on the quantum level, for chemists, it does just fine. However, there seems to be a preferred direction in which energy flows from one form to another. In order to understand why, we look at the second law. The second law introduces a new concept, entropy. Entropy is quite difficult to understand, but we can most easily describe entropy as disorder. And the second law states that the sum of the entropies of a system and its surroundings must always increase. In other words, the entropy or the disorder of the universe is always increasing. Within a system, there is also a tendency to go towards higher entropy. The classic analogy is that your bedroom will over time become messy, but it won't suddenly become neat. Another way to look at this is to say that entropy is a measure of how dispersed the energy of the system is amongst the ways that system can contain energy. Yet another way is to analogize entropic states to computer code. Let's take, for example, an ionic solid compared to the same substance as a liquid. Clearly, the solid state is more ordered and the liquid state is more disordered or higher in entropy. To describe the solid state using computer code, you would need to include terms that describe the geometry of the lattice, the intermolecular distances, the precise configuration of every molecule, and many other things. But to describe the liquid state, you would need to simply describe the volume of liquid and the shape of the vessel, because the motion and configuration of the molecules are random.
The scientists and engineers that support the next mission to Mars could be in this class.
Yeah, that could be. All right.
That's far less information that needs encoding, which is a way of rationalizing why increasing the entropy of a system is thermodynamically favorable. We can look at all kinds of processes to highlight entropic influence. Heat will flow from a hot coffee cup into the table or your hand because the heat energy will be more disordered if more dispersed. This is why heat spontaneously flows from hot to cold and not the other way around. Entropy. The third law states that a perfectly crystalline solid at absolute zero has an entropy of zero, as this is the most ordered state the substance can be in. Entropy is measured in joules per Kelvin. Note that entropy is not a measure of energy itself, but of how energy is distributed within a system. It is enthalpy, the thermodynamic quantity we learned about before, that is more accurately describing the energy of a system. As we will see, enthalpy and entropy intricately relate to tell us something about the Gibbs free energy of a system. G, or Gibbs free energy, tells us whether a process will be spontaneous or not, meaning if it will simply happen on its own.
Yeah. Christmas shopping.
Change in Gibbs free energy is given by this equation, which includes change in enthalpy, change in entropy, and temperature. If delta G is negative, the process is spontaneous. If positive, it is non-spontaneous. So we can use this equation to see how a spontaneous process can be either enthalpically or entropically favorable, or both, but not neither. For example, if delta H is negative, which means exothermic and energetically favorable, and delta S is positive, which means an increase in entropy, which is also favorable, a negative minus a positive will always be negative, or spontaneous. If the opposite is true, and both are unfavorable, we have a positive minus a negative, which will always be positive, or non-spontaneous. If only one of the two is favorable, we have to do some math. If delta H is positive or endothermic, that energetic unfavorability could be outweighed by the other term if the process is entropically favorable. And since T is here, this factor will increase with a larger T. So entropically favorable processes are more likely to be spontaneous at higher temperatures. Conversely, if it is energetically favorable but entropically unfavorable, the entropic unfavorability will be minimized at lower temperatures. This is a very important equation to understand because it describes all of the spontaneous processes in the universe. There are those who incorrectly use entropy and the second law of thermodynamics to imply that order can't happen spontaneously. But we just showed that entropically unfavorable processes can be spontaneous at lower temperatures if they are energetically favorable. An example of this is soap.
South by Southwest EDU is some form of education. It's
Tired of commercials.
technology and culture.
No. Lord have mercy.
Let's date here. Let's walk.
South by Southwest EDU.
It's fun.
Education, it's the possibilities of technology and culture.
Wash non-polar dirt and grime off your hands because they are immiscible with polar water molecules. But soap molecules have polar heads and long non-polar tails, which allows them to spontaneously form structures called micelles. These are spheres where the soap molecules orient themselves with the polar heads facing out in order to maximize ion-dipole interactions with water molecules that bring the system to a lower energy. And the non-polar tails will all face in, trapping the dirt by making a network of van der Waals interactions. The dirt trapped in the micelles washes away because the micelle as a whole is water soluble due to the polar heads facing out. That's how soap works. And that's also how highly ordered structures can form spontaneously if by enthalpically favorable or energy storing processes. In this way, systems can defy entropy on the small scale, But the second law does hold true in that the entropy of the universe is always increasing. Let's check comprehension.
Ah. I love the marimba. It's my favorite. I'll let him show you the answer. There it is. Spontaneous. All right, so let's review our thermodynamics that we had from physical science. So yes,
At the beginning that, the Bob conservation of energy didn't apply to the quantum scale. How does that work?
that is way beyond my pay grade. That's going to be if you do quantum mechanics, there's some stuff in there. We are going to talk about it a little bit because there is an entropy loophole that I have another video for, and I think it kind of touches on what he's talking about there, but that's like out there. Yes.
Does that mean that quantum level energy can be created and destroyed?
And no, I don't think that's quite what he means. But we'll, in a minute, when we get to the video about the loophole, I think you'll see, I think it's in that video. So who remembers these guys from last winter? Oh, they were so cute. These are our little Christmas winter rats reminding us about laws of thermodynamics. So we have thermal energy and matter.
I missed the.
Temperature is the average, what kind of energy? We said it already today. Colin, average kinetic energy of the individual parts within the matter. So all of the moving around. So this all links together. So in the past, we've talked about temperature being the average kinetic energy, right? And you're like, yeah, the particles are moving. All right. What? How does that relate to disorder? The more they move, the more disordered they are. The less they move, the more ordered they are. So the higher the entropy when the temperature is higher, typically. That also means there's more energy. So order / disorder, temperature, kinetic energy, these are all related concepts now. So if we've discussed one of them before or two of them before, now you should be kind of in your brain linking them together going, okay, this makes sense. All these things are related. So thermal energy is the total energy of all the particles. Oh, that's what we're talking about. All the particles. He's got his little thermostat there and he's got a little sweater. He's warm. Oh. What is the transfer of thermal energy from one object to another, Liam?
Heat.
Heat is the transfer, and it flows spontaneously from hot objects to cold objects. We said that last year. Why does it flow spontaneously from hot to cold? Professor Dave just told you. Why does it go from hot to cold? Jordan?
So the energy will spread out.
Yes, because if energy can spread out, it will. There you go. Exactly. If people can spread out in a room, they tend to spread out. You ever been on a city bus or a tram at the airport or anything like that? People don't all sit right next to each other, do they? They spread out until all the seats are taken. It's the same kind of idea. Okay, so what is an increase in the volume of material due to a temperature increase? What is that? Yes, it expands. Thermal expansion. Okay, so most things, when heat are added to the system, everything will expand. The particles within things expand. Then they start moving because the little bonds can't hold them there anymore because they're getting bigger. And remember that water is kind of an exception because it expands until it gets to a certain, when it's freezing water, it will freeze, it will condense, and then it expands when it gets to a certain point because it forms a lattice. But in general, things are going to expand. When you're driving down the highway and you're playing on your phone and you're going 70 miles an hour in your mom's car and you're hearing tick, 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 tick. What are you hearing? And why are those there? And not just earthquakes, because we live in Atlanta, it gets good and hot. And when the road expands, that concrete and asphalt will crack. So all those little rubber, those are called expansion joints. That's what they're there for. Same thing in a sidewalk. If you walk down the sidewalk in most neighborhoods, there's little breaks, right? It's not one solid, they could afford it that way, but it will crack because it will expand and there will be enough pressure that it will crack. So everything expands when it gets heated. And we talked about specific heat, which is the amount of energy in joules needed to raise the temperature of a substance by 1 degree Celsius. And we have a standard for water that you're using for a lab. So as thermal energy of a substance increases, the particles spread out and the substance expands. Why popcorn in the picture? PJ.
When it's heated and expands.
What expands? What in the kernel? What's causing it to pop like that?
The water more.
The water in the, yeah, when you put your popcorn kernels overheat or in the microwave, the water expands and goes from its liquid state to gaseous state, and your kernel goes pow, and you have popcorn. Yes.
Fun fact, it's only specific types of popcorn that can do that, not every.
Yeah, not every corn
I
is
tried
going to
looking
be
at-
properly dried.
5 corns a day, all.
Oh yeah, not everyone is going to be properly dried, and yeah. Does who likes caramel corn better than regular popcorn? Do we have a preference? We have a caramel corn crew here. I like them both. I like the Parmesan popcorn too, and the chocolate popcorn's not bad either.
I've had like.
What are you gonna say? Oh, nothing. You're just voting. What are you saying? Cheddar popcorn. I like the Parmesan popcorn, right? So thermal contraction and expansion. Thermal expansion is an increase in the volume of a material due to a temperature increase. So matter expands when it's heated, and this is what makes the liquid in thermometers rise. You saw it today. There was another thermodynamic law at work in your lab that you were probably completely not even thinking about, but you put that alcohol thermometer down into your solution, and as it heated, it expanded, which is what caused the little red line to rise up. There it is. What makes thermometers rise, and it's also the reason for the joints in the highway pavement. Thermal expansion is also used in what? Which contain bimetallic strips. This guy right here. What is this called? CJ.
Heaters, like space heaters or air conditioners.
Thermostats. Right. So a bimetallic strip is made of 2 different metals which are joined together. And these metals expand at different rates, and those rates are known rates, okay? And if one side of the strip, you got like one metal on this side and one metal on this side, and one is going to expand faster than the other, and it will cause it to curve, right? Kind of like, and next year this will come up, but this is the reason plants lean towards the light, because the cells on one side of the plant are going to grow faster and longer than the cells on the other side. And as they spread out, they cause it to bend towards the light. It's also the same reason that plants can wind themselves, like vines can wind themselves around things. It's using the same concept of one side expands faster than the other.
Someone assemble a thermostat and
And we sure did. And who was it? Who did we watch? Does anybody remember? Okay, this is the man. This is my man. He is probably the reason I got a STEM degree. Okay, I will never speak ill of Mr. Wizard. This is Mr. Wizard for those of you who do not know. His name is actually Don Herbert, but he went by Mr. Wizard. Definitely a Miss Danny childhood hero. I watched his show religiously. I have it all on DVD.
He's definitely not weird.
Yeah, definitely not weird. There is absolutely nothing wrong or nothing strange about random neighborhood children visiting a grown man's house all alone to learn about science stuff.
He's just giving them.
It's normal. They're just Canadian. That's all. Because this was a Canadian public television show.
There's nothing wrong.
And the whole concept is random neighborhood kids came over to his house. Hi, Mr. Wizard. And he's like, let me show you the science concept today, kiddos. And he taught random kids, sometimes more than one, sometimes just all alone like this dude. But man, did I love the show. So he's going to show you how the thermostat works. Never speak ill of Mr. Wizard in my presence. I'll never forgive you. He's the coolest ever. He's the best. He really is. 80s TV intro.
Recognize this, I assume, Danny, right?
Yeah, it's a thermostat that you put in your house to measure the temperature and the heat.
Well, you not only measure it because there's a little thermometer in here, but it actually turns the furnace on and off, right?
Yeah.
Well, you and I are going to investigate what goes inside there, and it's based on the idea of bimetal strip. Bimetal, meaning what is, you know what bi means?
It means two.
Two, right, two metals. In fact, here are two metals right in front of you.
Yeah.
They're two wires made of metal. And I'm going to send electric current through them to heat them up.
Okay,
Heat it down and sight right across those weights that are on the top there.
okay.
And watch what happens as we heat up the two different metals. What's that?
Well, the one in the front, it's sinking down, like
Right.
making much more
Okay.
wires.
Now watch, I'm gonna turn off the current. Go back up again?
Yeah, they're right back up to like the same level as the.
As it cools off, it will go back up to the same height as the other one. In other words, what I did this for was to show you that metals expand, but different metals expand at different rates. Obviously, the one on the front expanded the most,
Yeah.
right?
Mhm.
Okay, now let's assume, right over here, and light the candle.
Okay.
And let's assume that we take two metals and put them together to form one strip, which is what this is.
Okay.
You light the candle. Okay,
He's a pro.
okay, put it right down there. Now hold the strip right in the flame of the candle and watch what happens.
Hmm. It's starting to make an arch upwards. It's making a
Yeah.
really
See
big
how it's
arch.
going up?
Look how it's bending.
Yeah, bending a
Wow.
lot. Right.
Yeah, because of the heat.
Okay, now you can blow out the candle. Okay, now what happened was we have, that looks like one metal, but it's actually two metals put together, like these two pieces of wood.
Okay.
Okay, now watch what happens if I expand the bottom. Watch what happens to the whole thing.
Oh, it's making an arch up right
Yeah, it
here.
makes it go up.
Yeah.
That's why that went up,
I see.
because the bottom piece of metal expanded more.
Yeah.
Now let's assume we take this piece of metal and form it into a coil. Okay,
Okay.
so go around over here. I have a thermostat all set up on this little piece of wood. Can you find the coil?
Oh, there it is, I think.
Yeah,
It coils
That's
up
the
around
coil,
there.
right, there's the coil made out of that bimetal. And at the moment, notice that there's no current going to the furnace represented by this light bulb, okay? So we want to cool off the room in order to make the furnace come on, and you do it here with this spray, go ahead. Push down on the top, and out will come a spray of gas, and you will cool off the coil. There you go,
Wow. it
on
cools
to the
off.
furnace, right? Okay, now, this is the furnace, so turn on the blower and hold it at the coil. Okay, now, the furnace went off.
Yeah, turn it off.
Now, this time let me handle it because I want you to watch right there, right at the end. See, I put a pointer here?
Yeah.
Right at the end of the pointer, watch right there. Right now, that's a switch and it's open.
Okay.
Watch what happens when I cool it off.
Wow, the switch moved down towards here and
Right.
it
And
expanded.
made it connected, right? Made a
Yeah.
connection
Mhm.
and sent current over to the furnace, which now comes on. Now watch what happens to the switch.
It moved up again and the current turned off.
Right. So now you know
Wow.
how the thermostat works. What do you call the thing inside? Bimetal?
Metal.
You're right.
Coolest person ever, man. Mr. Wizard is the best. Very cool. You can binge Mr. Wizard on YouTube, man. I sure can. Yeah. I'm not sure, actually. Yeah, that would be a good thing to look up. I'd be curious what's in him.
Exactly how I think a Canadian old man would say.
Yeah, he's amazing. He's very cool. He did one once that I loved it, and it was about pressure. But he had, and I'll never forget it because it was super cool. But he had giant like jars or jugs of, I think it was grape juice, down on the ground, and then he was way up, like 2 or 3 stories up on a balcony. And he had 2 straws. He had one that looked like a regular straw, but it was just really long, but it was about the, diameter of a regular straw. And they had another one that was like this big. And he tells the kid, he's like, all right, suck that up. Which one do you think's going to be easier? The big straw or the little? The kid's like, oh, the big straw. No, you can't do that. There's so much more air that you have to get out of the way. That one and the one where the allowance one, and you could try this, but your parents are probably too smart. But it was basically this. It was about exponents and how they work. And not just exponents, but really not exponents, squaring, really. Because what he said is, tell your parents that for allowance, they can pay you 1 penny on day 1. And then they double that on day 2. So it's only 2 pennies. Then on day 3, it's 4 pennies.
And the
They-
journey is like 5 minutes.
Yeah, and yeah, it gets really big really fast when you double. So that's, anyway, it was a fun one. He made the whole potato battery, you know, all the fun stuff. He cooked lunch outside in an umbrella oven with aluminum foil and an umbrella. It was so cool. Anyway, so let's have a look at our different scales to kind of refamiliarize ourselves. So you have Celsius, Fahrenheit, Kelvin. You also have Rankine and Ramure, but we don't use these very often, but they do exist. But it gives you some idea of where on the scale you'll find these things. So like room temperature, 21, 69.8, 294, right? So we tend to think of it as close, a little closer to 70. So that's a little higher as we go across. But like body temperature, like your doctor will measure your body temperature often in Celsius. 37 is normal. It's the same as 98.6. So yeah, keep in mind that there are more than just those three, but these are the three, the big three that are going to matter to us. So Fahrenheit is most used in the US. The rest of the world has moved on. We have not. Water freezes at 32, boils at 212 because that makes sense. Whereas Celsius, you've got the 0 and 100 and it makes sense, but we refuse to give it up and we're America, so we're not giving it up. Yes.
Where do they use the last?
You know, I'm not even sure specifically what specific disciplines of science use those, but it's apparently more secure. Yeah. What? No, France. More obscure is the word I'm looking for. Brain. So the Celsius scale is pretty much everywhere else in the world and in science, and it's 0, 100, which makes sense. And then Kelvin is used in physical sciences and obviously in chemistry too. And then your water is going to freeze at 273.15 and it's going to boil at 373.15. But the whole point of Kelvin is when you're dealing with thermodynamic concepts, right? You have to have a concept for absolute zero, and that's the purpose, right? And remember, at absolute zero is theoretical because it's no motion of particles, and we can't accomplish that. There's always some level of motion of particles. Even in solids, they're vibrating, right? So specific heat. So it's the amount of heat needed to raise the temperature of 1 gram of water by 1 degree Celsius. Yeah. Yeah, it's your specific heat. Yeah, that's what it says. So if you're trying to, and we talked about how there were some standards that we know, some standard values. There's your water again. Remember, we talked about it today? There it is. There's your solid water and ice, your water vapor, basalt, granite, iron, copper, lead. We know all of these. Okay, we have all of these. So be aware, some standard values are just standard values and we already know them. Calorimeter, that's what you use today. It uses the principle that heat flows which direction, from what to what? In what direction does heat flow?
Hot, cold.
Hot to cold. That's right. From warmer objects to cooler objects. Always, always. That's the whole point. Okay. Until they both become the same temperature. What do you call it when the objects reach the same temperature or same energy level? What's the word there? It's equilibrium, right? It's kind of what you're looking for, right? All right. So heat and thermodynamics. Thermal energy and states of matter. All matter on Earth exists in 3 states: solid, liquid, gas. Yes, we have plasma, but these are our main on Earth under regular conditions. A physical change from one state of matter to another is called what? PJ?
A stage change.
Yeah, state or a phase change. Yep. So matter will change from one state to another if thermal energy is absorbed or released. So if you're absorbing energy, and if you are liquid water and you were absorbing energy, what are you changing into?
Yeah.
Right. And if you are releasing energy, what are you turning into?
Oh, ice.
Ice. That's right. Okay. So our calorimeters that we use today. So what's the transfer of thermal energy with no overall transfer of matter? So this one is going to be conduction. We've transferred energy, but we haven't transferred matter. Conduction in gases is slower than in liquids and in solids because the particles in gas collide less often. What do you call a material that conducts thermal energy well, Caitlin? A good conductor, right? A good thermal conductor. Thermal conductors and electrical conductors tend to be the same, tend to. And a material that conducts thermal energy poorly is? An insulator, right? A thermal insulator. What's an example of a good thermal conductor? Sander. Iron? Is that what you said? Yep. Okay. What's an example of a good insulator?
I
Oh,
don't know.
what were you gonna say for conductor?
Copper.
Copper's a great one. Yes. How about an insulator, Colin? Rubber's a good insulator, right? Okay, good. So we found purposes for all of these in our day-to-day life. All right, convection. The transfer of thermal energy when particles of a fluid move from one place to another is convection. Where in my 4 courses do we talk the most about convection? Earth science, because of what? Drew? There you go. Convection currents in the mantle are what are responsible for moving the tectonic plates. The fact that we've had continental drift, the fact that Earth looks the way it looks, the fact that, you know, continents used to touch with a Pangea, it's no longer a thing, is entirely because there are convection currents within the magma under the surface of our crust. It's constantly rolling and moving, and those currents cause the tectonic plates to move around. So that's convection. So what occurs when a fluid circulates up in a loop? This is convection current. That's what it's called, right? It goes up and down. That's what's happening right there. You see the lava lamp, and it's still kind of cold, but when you see that wax blob go up, it's because it's heated, it's expanded more, it becomes less dense, it goes up. When it gets to the top, it cools, and then it falls back down because it becomes more dense, and that's a convection current. And we have them in natural cycles everywhere: ocean currents, water systems, movements of hot rocks in Earth's interior. Lastly, we have radiation. So it's the transfer of energy by waves through space. So all objects radiate energy. So the crystal people aren't totally crazy. All objects radiate energy. You know, the people, oh, it's got good energy. Everything has energy. So all objects radiate energy. As an object's temperature increases, the rate at which it radiates energy will increase. All right, so here's the picture. We have convection, conduction, and radiation occurring all in this picture or represented in some way. So what we see, click, I said click. Come on, click. What's happening there? Xander. Oh, I'm sorry, Lucas. I thought your hand was by your head, but it's not. That's actually the, all right, Lucas, what is it?
Fire.
The fire. Okay. Your fire. Fire is going to give you radiation. Yes. Oh, yes. That's your radiation heat is fire. So sometimes I use a little graphic on my exams, and it's like a little campfire with a little pot over top. So this is very similar. So this is radiating your heat. What do you suppose is occurring within the pot, Escher? Conduction, not conduction, convection currents, because you've got the stew that he's making. He's hungry. He's making some stew. The stew is getting hot at the bottom, and then it rises to the top. And then when it gets to the top, it cools off and it falls back down, and you have convection currents. And then why is he wearing mitts?
Conduction.
Because of conduction. What'll happen if he's not wearing the mitts? He will burn his little rat hands. Now, mind you, he is standing on the stove, which I do not recommend, but still,
I do that every day.
his little toes are probably his right foot's probably real hot right about now. But I actually had an experience with both radiation and conduction on Thanksgiving Day. I had a pot on the back burner that I had sat there that I was going to put stuff in. I just hadn't put it there yet. It was just an empty pot, and I put it there. And then I thought, it's in the way. And I reached to grab it, and the burner was not on, but the burner next to it was on, and the heat had radiated enough to that pot that when I touched it, it was real hot. So it radiated, and then it conducted into my hand. And I was like, woo, and said a few choice words and dropped it. And my mother's like, are you all right? I'm like, yeah, fine. I'm gonna have a little, and I do have a little rough spot on my thumb, right? So yes, convection, conduction, radiation. So in thermodynamics, which is the study of conversions between thermal energy and other forms of energy, we have our 3 laws here. The first law is what? Do you remember?
Energy is not.
Yeah, it's energy is conserved. That's the big one. Energy is conserved. What's the second law, Jordan?
People flow from hot to cold.
Yes, energy flows from colder objects to hotter. Oh, that's the one that I didn't change from last time, hotter to cold. Oh no, that's right. I'm not reading the whole thing. Oh, colder to hotter only if work is done on a system. So without work being done on a system, it will naturally flow from hot to cold. If you do work on a system, you can get it to flow the other way, but you have to do work on a system. The third law is what? TJ.
If A equals B and B equals C, then A equals C.
Yeah, that's not third, but you're almost there. It's absolute zero cannot be reached. We just talked about that. But that is going to be which law? The zeroth, my favorite law. The zeroth law. Why they just didn't do fourth?
Because they're
Well, where's the fun?
I know, but you remember this because never in your life are you ever going to use zeroth except when it comes to this. Like,
Like it's talking about all the way.
it's talking, yeah, maybe because they're like, oh, we'll just back up. It's the prequel, it's like the Phantom Menace or one of those. It comes way ahead of the trilogy. All right, so anyway, the prequel. So it states that this is what you were saying. If A equals B, two thermodynamic systems are each in thermal equilibrium with a third one, then that means they are in equilibrium with each other. So if A equals C and B equals C, then A equals B, right? If A equals C and B equals C, then A equals B. So any object that converts heat into work is called a heat engine. And heat not converted into work is called waste heat. And I have that Stirling engine up there. This guy. Where'd he go? Where is it? Oh, right here. Great example of a heat engine. Do you want to nuke a cup of water, Drew, so we can watch it go and watch people's ears screech again like last year?
Yes, sure.
This is interesting because so there's a diaphragm in here, and as the air in here is heated up, the diaphragm will expand and it causes the wheel to go. This is called a Stirling engine. You can see it's like a piston, right? But it was funny because last year I put it out and apparently it makes a little squeaky noise that only some people could hear because it was so high pitched and other people couldn't hear it. Like, I'm too old, I couldn't hear it. But it was it was kind of funny because a couple of people were like, what is that sound? So we will. So thermodynamics, but why? Entropy. So entropy is central to the second law of thermodynamics, which states that entropy of an isolated system left to spontaneous evolution cannot decrease with time. As a result, isolated systems evolve toward thermodynamic equilibrium where entropy is highest. Okay, I got it, but wait. All right, here's our loophole. While the water's heating up, we'll watch this loophole video. This one's fun. This one's like theoretical fun. Why are you not playing? Yeah. You're a nerd.
Like this.
When you study physics, they teach you a bunch of rules. Things like how you can't create energy, you can't travel faster than light. It's like, stop telling me what to do, man. These rules are helpful though, because they give you a framework for how the universe works. Like, no matter how complicated things get, at least it's not a lawless wasteland out there. Except there is one law of physics that's fundamentally breakable, even though scientists don't usually treat it that way. The second law of thermodynamics. To put it simply, this law says that a system will never become more orderly on its own. The amount of disorder will always increase or stay the same. It's a cornerstone of physics, and it tells us how everything from car engines to galaxies should behave. But if you look closely at it, you can see that it's a law that was made to be broken. And for the world of nanotechnology, that could lead to unexpected consequences. Although you might have a pretty intuitive idea of what disorder is, like if you've looked at your sibling's bedroom recently, scientists have a more specific way of thinking about it. They measure the amount of disorder with a concept called entropy. Entropy can be considered a measure of randomness, or how orderly a bunch of particles are. But it can also be considered the amount of energy that's unavailable to do work. Like imagine running a car engine. No matter what you do, the engine will always turn some amount of fuel into waste, like heat. This is unavailable energy because it can't be used to make your car go forward. According to the second law of thermodynamics, the longer you run your car, the more unusable energy you'll get. In other words, the more entropy will increase. This observation is actually what led to the discovery of the second law in the first place. Although it was discovered in the 1800s, so it was about steam engines, not cars. And today, we know that concept applies everywhere. It's why engineers still can't make a perfectly efficient machine. And on a much larger scale, it's why the universe will eventually run out of usable energy. It's even why the layers of milk and espresso in your cappuccino will blend together if you leave the cup out long enough. The two liquids might start out all neat and artistically separated, but they'll eventually become more random and will mix. Essentially, the second law says that entropy will never decrease on its own. Even if you do create order in one system, you'll always create disorder elsewhere, like by generating heat. But for as confident as this law sounds, it isn't bulletproof. If you look closely at why the second law exists, you start to realize that it has a pretty big loophole. At the most basic level, the second law is true because molecules move around randomly due to their thermal energy. And they're equally likely to move in any direction. Ultimately, this means there are way more opportunities for particles to end up disordered than ordered. So disorder is more likely to increase. Think about that cappuccino again. There are probably around a few septillion molecules. That's a 1 followed by 24 zeros in that drink. And there are only a few ways those molecules can be arranged so that all of the milk is on one side and all of the espresso is on the other. So assuming one arrangement is just as likely as any other, the odds of your cappuccino getting more orderly are really, really tiny. But the thing is, really, really tiny is not quite impossible. It could happen. Of course, the odds of this happening for a cup of coffee are so slim that they're kind of ridiculous. And they don't mean much to physicists. That's why the second law can so confidently say that the entropy of a system never decreases on its own. But in reality, that law is just a statement about the statistics of particle motion. In other words, it's so likely for entropy to increase, or at least stay the same, that we can functionally say it does it all the time. Except for small systems, we can't assume that. And by small, I don't mean systems of like 2 atoms. In recent decades, scientists have found that in systems of up to 100 particles, it's not too unlikely for random chance to decrease entropy, just for a little bit. One of the biggest experiments came in 2002. When Australian researchers published evidence for entropy decreasing in a collection of micrometer-sized beads suspended in water. The random thermal jiggling of water molecules was constantly pushing the beads around, and for the most part, as expected, the beads were moved randomly. But then the researchers looked harder, and they found that sometimes, by pure chance, the beads were pushed in a specific direction, causing them to noticeably speed up. In other words, the beads were turning the disordered random heat energy of water into ordered kinetic energy that can do work. And it was all for free. This effect only persisted for a few tenths of a second, but it proves that on a small scale, you can cheat the system, at least briefly. This wasn't the only paper to investigate this idea either. There was another in 2005 that suggested these effects might be present in photosynthesis, and a few more from 2013 and 2016 that explored how this might apply on the quantum level. So it's something researchers are actively exploring. While this might sound like a random technical detail, these studies are actually really significant. Because as nanotechnology continues to develop, we're going to be building things like engines and transistors on these smaller and smaller scales. Realistically, this loophole in the second law doesn't mean we'll be able to make a bunch of tiny 100% efficient engines or anything. But it does mean they might sometimes pick up energy from their environment, or their molecules might move differently than expected. And that's definitely important for us to know. The rules developed back in the 1800s will have to be rethought to control things at these tiny scales. Otherwise, we might be in for some surprises. Thanks for watching this episode of SciShow. If you want to learn more about the laws of physics and how they apply to the world around you, you could.
So Lucas, that was like your question. You act like, when is energy not conserved? When does the law of conservation of energy not apply? So it's kind of like what they're saying there with the water molecules. So if they're not moving randomly, if they're suddenly moving in an order and together, they're creating order, but they're creating order. It's the kinetic energy that's involved in that order. And typically that involves work being done on the system, which means energy is added to the system. But in this case, it was like energy's added, but it's almost like it's created within the system, I think is what they're trying to describe. Does that make any sense? It's hard to explain. But if you really think about it, like you have to do work on a system to create that order, and somehow there was work being done. So there's energy that somehow sort of created on a quantum level, but maybe not really. Like that, like I said, above my pay grade. But I think that's what he was hinting at. So let's real briefly talk about using heat, and then we'll be sure we go over what you need to have ready for next week. So the two main types of combustion engine, the external combustion engine and the internal combustion engine. The external combustion engine is an engine that burns fuel outside the engine, like a steam engine. And an internal combustion engine burns fuel inside the engine, like a gasoline engine. Does anybody remember what we did last year with the little paint can? Okay, what did we do with the paint can? We blew it up. We did. We took a few drops of gasoline and we put them in we had a paint can with a lid on it, and we had a little hole in the bottom. And we put a few drops of gasoline with the lid off, and we kind of twirled them around in there, and then we put the lid back on. So now that gasoline is very quickly vaporizing, because that's what gasoline does. It vaporizes fast. And then we put it on a ring stand, and then we put a little flame underneath of it, and kaboom, because that caused immediate thermal expansion, which caused the top to come off the paint can and the paint can to move. And that's exactly what happens within your internal combustion engine in your car. That's how the piston is pushed up. Like in this case, you see it working with the heat below it, but that piston that moves up, that turns your drive shaft, it's because you're having little tiny explosions inside the cylinders in your engine, right? Right, that's how they work. So central heating systems, like you have in your house, remember, heat many rooms from one location. Most heating systems use convection to distribute thermal energy. Hot water heating, steam heating, electric baseboard heating, and forced air. Most modern homes have forced air, but if you've been in older homes, some of them have baseboard heating or radiator heat. Radiator heat, I love. And the reason he has a mallet is because if you have radiator heating, it gets like air pockets in the system, and it creates a very loud banging noise. And the only way to make it stop is to like whack the radiator with a rubber mat. I had my dorm room, my junior year at Hollins, had a radiator, and it's all on a central boiler system. So it's being piped underground like all over campus. But I'd be asleep and it would go bang, 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 bang. And I'd get up in the middle of the night, like whack it with a rubber mallet, because it was very, very loud. So heat pumps reverse the flow of thermal energy. Heat pump is a device that reverses the flow. Refrigerants are fluids that vaporize and condense inside of tubing in a heat pump. So heat pumps must do work on a refrigerant in order to reverse the flow of thermal energy. Refrigerators are a type of heat pump. This is why when you're behind your refrigerator messing with it, if you go back there, it's nice and hot, right? The heat is coming out of the back. So air conditioners remove heat from the air. Let's look at your answers real quick. I'm just going to click through them if you want to check them, and then I'm going to show you what's on your midterm. So the property of a system that makes a process occur consists of two driving forces: the tendency towards the greatest entropy or disorder state and tendency towards the lowest energy state. The quantity of entropy possessed by 1 mole of a substance is called its standard entropy. The symbol for standard entropy is that lovely little S. And the units are joules per Kelvin. Joules Kelvin, sorry, per mole. I couldn't talk. Joules per mole Kelvin. I told you my brain is dead today. Same as for molar heat capacity. The thermodynamic quantity used to predict whether a reaction will occur spontaneously is our Gibbs free energy equation. And it's defined by the equation G equals H minus, it's T delta S really is what you're looking for, is the delta S. The reaction is more likely to occur if the change in enthalpy is positive. An entropy of a substance increases with temperature. Gases have greater standard entropies than liquids. Gases have the most freedom to move, so their standard entropies are greatest. At absolute zero, no disorder means no entropy. The entropy change of a reaction is standard entropy of the products minus the standard entropy of the reactants. Because the atoms in a diamond are more ordered state than in graphite, the change in entropy in changing graphite into a diamond is negative. Your midterm. Pay attention to your email this week. It's going to tell you exactly what you can put on your 3x5 card. These are the topics. You've seen this list before because I think it's at the front of your packet. Has anybody started their midterm packet? Hopefully most of you have started your midterm packet. If you do your midterm packet, you'll be ready for next week. Next week is review. We do have a lab. It's a short lab. It's not a write-up lab, but we will do a quick lab anyway because it's fun. It's a fun lab we're going to do. But next week during class, we will do the review with the reveal answers, which looks exactly like your midterm review packet. So if you have it in front of you, you should be able to answer all those questions. We will do Jeopardy, and we will very likely also do Sink or Swim, which I have set up. We didn't get to do Sink or Swim for our final last year, and it's a lot of fun. So, excellent.
Can I be tested on the water?
Can you be tested on the water?
Just thinking.
Sink or Swim is fun. Wonderful. Read this week's email. Make sure you know what's going on.
We all know what's happening with you.
Very nice. Hope you do.
Honestly, you're really skinny though. No.
Really skinny people sink.
I sink. I want to show you what I'm doing.
Andrew, you're just so heavy. You're so heavy, you say no matter what.
So
these are so cute. You're making these, or they're in your advent calendar? What calendar did you get? It's so
little 3D pins of like 20 cents.
That's adorable.
So I just wanted to show you.
Because they're cute. I appreciate you showing me. They're way cool.
So much.
I for real need a 3D printer. I know I will use it. I just haven't gotten there yet.
I have a 3D printer. If you get one, don't get the Ender Pro 3 because it's such a pain to level the bed because you have to do it every time.
Okay, good to know. I'll keep that in mind. Yeah. This one for the whole team. Yes, it was. That's the one. Yes, that's the one for the whole team. Be proud about it. And you'll end up as cool as me. I own my nerdiness. It's all good.
I'm a nerd about completely useless topics.
I am too, about a lot of completely useless topics. I'm also very picky about certain things. Jason says I'm a lyrics snob because I'm constantly correcting him because he sings the wrong words to songs. I'm a big nerd about that.
I somehow find almost very fun.
Those are helpful though. They're fun. You can play Jeopardy one day.
Yeah, I have child.
Uh-huh.
Your oxygen levels to 17%. If you're 7 or 17%.
I wear them all the time in high school. Yeah. Weird. That's a fun one. I love random facts like that make you go, huh? Wait, what? Explain some things about certain people.
You see all the lab rats in different study topics?
Mm-hmm. Oh, yeah, that's what, right, yeah.
Chemistry is way tougher than
Yeah, chemistry is the hardest one. You can get through this class well, you can do any of the others just fine. This is the hardest one, I think, at least in my opinion. The hardest one for me to teach, so. I will in a minute. He needs to let everybody go. I can't, it kills me because he loves you guys. He gets excited. He gets excited when you come, but I can't risk my buddy. What?
No, I'm just saying the scientist's name.
Oh,
Yeah.
who?
Ernest Schrödinger.
Rutherford? Ernest
Oh,
Rutherford.
yeah.
Yes.
Erwin Schrödinger.
Erwin, yes, Erwin Schrödinger.
I don't know why, but Ernest Schrödinger is my favorite.
He's a cool dude. They're all cool dudes. An interesting history.
The field is almost officially over.
I know, I gotta get more. You guys
Not
still
more
want
skills, more M&Ms after.
I like the M&Ms too, but you have to be careful with them because the non-peanut M&Ms, they make in the same factory as the peanut M&Ms. So if people have peanut allergies, they can be really sensitive to
I
them.
don't think there's anything feel either, right?
I have to double check my list. We might. I tend to just try and keep away from it.
I love peanuts raw.
Oh, for real.
Roasted.
Honey roasted?
Not honey roasted, like.
Or just regular roasted?
Yeah.
I like honey roasted too. The roasted.
And then
yeah,
I add
different.
like some spice to it.
Yeah.
And then I love eating them.
Yeah, my dad. Have you ever had boiled peanuts?
Boiled?
Yeah, that's a southern thing. They're on a, you can find them. You can find them at like racetrack. And you can also find them on the side of the road in the mountains. There's always some like old grizzled
I
dude.
think my parents have them. I don't think so.
They're really yummy. They become like almost like the texture of beans, but they're tasty. I think they're delicious. My mom won't eat them. She thinks they're gross, but I think they're delicious. These people not using any water.
You know the jackfruit seeds?
Yeah,
I used to my parents boil them and eat them.
really. I've never done that. I've had jackfruit, but not the.
I love
seeds.
jackfruit.
Did you?
Yeah.
The only place I ever see them is like Patel Brothers or like Super H Mart or something.
Tail Brothers?
Yeah, you go there?
Yeah, I go there.
I like that. I like, you know what, you can get the least expensive nuts at Patel Brothers. Like they have almonds and cashews for like really inexpensive compared to like Walmart or wherever.
Or we go to Mountain.
You go to what?
It's like a store in Buford.
Okay.
And then we buy jackfruit and
Ah, I've gotten jackfruit at Patel Brothers and I've gotten rambutan.
Orangutan?
Yeah, the little red ones.
Oh yeah, those
Love
the
them.
spiky ones.
Yes, like little lychee almost,
Yeah,
like
yeah,
those
yeah.
are really good. I like them. And when I go to Patel Brothers, I get nuts. I love the nuts, like I said, they have really good nuts and they're inexpensive. And,
When like I thought that is one of the stores we go.
there's a new restaurant, if you're looking at Patel, newer.
Honest? Is it called Honest?
Yes, the right.
Left.
No, Honest is to the left, I haven't been in there. The one that's to the right. Yes, it's excellent. So good.
What's it called?
I can't remember. I went, so my choir director, we're really good friends because I've been in the choir for 20
What
years.
is famous over there?
Famous over where?
At the place. Right.
Your
favorite. What's famous over there? What's it good for?
Just the food is really delicious. Like
You
we
know,
went,
I did you find?
I can't even remember what everybody had.
Isn't it Indian?
No, it's Indian. It's Indian restaurant. Yeah, it's right. It's next to Patel.
It's like a superstar.
What it's called.
There's a lot of.
It's right next to, it's to the right of Patel Brothers. And anyway, we went there, we took him, his favorite thing is Indian food. He loves Indian food, cooks Indian food.
Is he Indian though?
No, he's very white, but it's his favorite thing is Indian food. So,
Indian.
and he has taken the time to like learn all the traditional recipes and everything, like he really likes it. So, it's for sure his thing.
There's Indian food called samosa.
I love samosas.
I love them.
I love samosas tons. I will eat samosas and be very happy. And have many times eaten samosas
It's
and
like-
be very happy. They're delicious.
It's
I had my first samosa in San Francisco.
San Francisco.
Yeah, and I-
California?
Yeah, and I don't think any of the samosas I've had since are as good as that one. But those were really good. Yeah, no, my one of my friends, she was one of my bridesmaids, and she was one of my husband's really good friends from college. She's Indian. So when we went to visit her in San Francisco several years ago, she took us to this restaurant. She's like, they have good samosas. And I'm like, all right. And I never had one before and they were unreal. They were so good. They were unreal. So I very much enjoyed that trip. She's a lot of fun.
I think the last time we ate samosa was like, a few days ago.
Oh, yeah. I love good. Good samosas are good. I like, I forgot what the other thing was.
My sister gives like the inner part to me and eats the outer part,
Oh, yeah. She likes the crust. Yeah.
the crust.
I like, when I go to Indian restaurants, I usually get chicken tikka masala, that's my favorite. That is my favorite, although I do get butter chicken sometimes too, but I like chicken tikka masala best, I think. I think that's kind of how I judge an Indian restaurant, it's how good is their chicken tikka masala. I really do love it. Yeah,
They're long.
I don't see three here, I see three. Oh, it's probably in this bin. Yeah, there it is. Excellent.
Yes.
Thanks. But yeah, I do like, I like that new restaurant over there, it's pretty good. My, favorite. I haven't been to Honest, is it good?
Yeah, it was good. I
Okay.
had some samosa there too.
His favorite restaurant is Bukhara. Daniel, my choir director, that loves Indian food. Bukhara is his favorite, and we've been there a couple times.
Bukhara?
Yeah, Bukhara is over, St. John's Street. And it's,
I've never been
they're
there.
excellent, I love Bukhara. But he's the one who told me about Bukhara, so the first time I went was, because he told me it was good. And he's right, it was real good. It was real good. This is still warm. It's fine.
There's a shop called, like, Street Krishna Block, have you been there?
Where is it?
Street Krishna Block.
No, where's that?
It's somewhere near,
Is it food, grocery store, or?
it's a restaurant,
It's a restaurant, oh, okay.
yeah,
It's
it's an Indian restaurant.
I like, so my favorites are now that place I can't remember the name of, that's next to Patel Brothers. I like Rom. At the, up
Oh,
at the
yeah,
corner.
yeah.
Rom is good.
Like that. Near wrong, there's this thing called World Champion.
Yeah, I think so. Is that what you do? Okay, yeah. Rom is good. Indian Flavors, which is just around the corner from that. It's in the it's next to the Publix that's up there. That's very good too, and they're like, they have a couple little seats, but it's more like a walk-in and takeout. I do that, I love that one. But I like,
Do you have a hobby on to Indie Fresh?
no, where's that?
It's in, you know the Buford Highway? Well, you know
Out
the
there.
Ariana's?
Yes.
Ariana, and then there's this highway.
Okay, it's over
Yeah.
there.
Yeah,
Can
you
try
turn,
that
and
one.
then you turn, you know, Ingles, like, the Ingles, you go straight on Ariana.
Yes. I
There's an
do.
Ingles, you turn right on the Ingles, and then you go straight there.
Okay,
And
yeah.
there's-
Okay, I haven't been there yet. I did go to Ada. Ada's out on 141 in Johns Creek. I did not like it. It was crap. It was terrible. It was supposed to be like pub food. It was gross. I was unimpressed entirely. I'll shop, like I said, at Patel Brothers. That little place that's next to the Kids Are Kids and Sharian's.
Charians, yeah, Charians.
I go there.
My dad goes there every day.
Does he? They've got good stuff. I go there. I've gotten stuff there before. Yeah, I'll be the random white lady walking around Patel Brothers or I try anything. I like all kinds of stuff. I like the opportunity to try different things. So I do when I can. And I do really like them.
Charians, you know Subida?
Where's that?
It's like right in front of Charians.
Oh yeah, I haven't been in there. I've seen it, but I haven't been in. Is it good?
Yeah,
There you go.
pretty normal.
So
You
there's
also buy samosa from Charians too.
oh, I haven't had their samosas. I've only had the ones that
Really?
Patel Brothers used to have.
I think we bought samosa from Subida, not from Charians.
Oh, okay.
But we bought this like the pack with samosas from Charians.
Got it. Yeah, my there's another man that's in my choir. He's Korean.
Korean.
He's Korean.
Interesting.
And he's so funny. We were like, hey, Mark. Because we have a Christmas party every year. We're like, you know what? You have your own kimchi, right? Which is like a
Kimchi.
yeah. And he's like, yeah, we have a family recipe, we make it. And we're like, so you want to bring some to the choir for me? He looked at all of us and he's like, you wouldn't like it. It's really spicy. And we're like, try us, Mark. Try us. So he brought it one year. It was so good. And I said, did you help make this? And he's like, no, Margaret, his wife. He said, I stand in the kitchen and Margaret goes, get this, get that. And I get this, I get that. I don't make it. He's one of the sweetest people I know. I absolutely love him. He's a dear friend. So. And he has the cutest granddaughter on the planet. Like this baby is, oh my gosh. And she knows it. Yeah, she's very sweet. Her name is Donnie. And she's.
You know, inside Charians?
Yeah, been in there. Our whole family went in. It was funny. It was years.